sign in to our attendance, right? I cut and paste into the notes on your right hand side, right? You go there and just fill it up, right? But make sure you have your student name and your matric number and your name there, right? The rest you can and your class. I don't want to get mixed up with other classes as well. So the three um, um, answers you have to actually fill in, right? And it be recorded, right? There are other classes, so same thing as well. Okay. Please, right? Key in properly, right? Don't just simply key in, especially your class, otherwise you get mixed up. Right. Okay, I hope I can finish this within the time frame. As I mentioned, the recorded lectures I'll share with you as well with this one, right? As well as with this one. And another thing I want to mention is with regard to we need some assessment. So I have video, right? I just write here assessment. So we have video. This is short. This is in Edpuzzle. Edpuzzle. So you need to register. Sorry, my brain and my hands lack of coordination. Edpuzzle.com. So if you go to edpuzzle.com, right, you register there. Okay. Right. So there are video, right? The video is no skipping, right? As I mentioned before, right? You just answer, then move along, right? Okay. And then secondly, we have short questions. Right? This one you just answer. I'll pass it to you. All right, I'll pass it to you. This one in a Google form, so you just answer straight. Right? This is open, right? This one open. Okay. This one no skipping. This one is open. Right? So I'll let you know. Maybe we have this is week 5, week 6, week 7. So we need times in between, but you have extra notes over here. Right. So again, please key into your sign in your attendance, please. Okay. Right. The images, some extra images actually slightly different from your lecture notes, and I think I mentioned earlier on. While waiting for your class, 9 o'clock, I arrived much early today. By 7:30, I'm in the office. I record your lectures, and I managed to yesterday also just paste in some of the new images, but they are the same. Just give a nice image compared to before. The text is almost similar. There's not much variation. I think the texts are the same. Some images, I put the extra images and so on yesterday. This morning, I made recorded lectures for you. So beside this one, today lectures, if you cannot finish, all right, I try to upload to the recorded lectures. Okay. Actually, one of the websites that I had much earlier in my career in 2000, last year, see how many years is that? Actually the website is up again and I can log in. So, it's free. So I'm going to put all the lecture notes in there as usual, like I did in year 2000. Okay. I start online since year 2000. Okay. But that time, not quite accepted, not quite accepted. Before you have this e-learning system, already have my website, right? Dr. Munira, I can remember that. So I have my own website, and all lectures is actually online. So you heard of Dr. Munira, your lecturers. So I think she still remember all those lecturers from Jabatan Kimia. Still remember that. Okay, so that website is up. So I'm going to put. Doesn't matter it's long, but you can always download compared to our Spectrum. So going back to our lecture today, right, on bioluminescence. My apology, because I noticed that some of the text actually, because my tablet doesn't have that software or doesn't have that extension link, so it actually I cannot have the same formatting, okay, in my computer and in my tablet. Okay, what is bioluminescence? Right, luminescence. This is light emission, light emissions. Right, light emission that does not involve any heat being generated. Right, heat being generated. So on the right hand side we have a jellyfish. Okay, we have the jellyfish. This is remember the David Attenborough. Well, he passed away, of course. Um, and this is very nice luminescence image, bioluminescent image from a jellyfish. And the bottom image, right? This is a shark. Right? You notice that bright green luminous emissions from the shark. Okay, this is a cat shark. We call it cat sharks. Okay, so what does it actually? Why the bioluminescence is important, especially for animals, for living organism, right? For coral, for instance, so I just take example for coral. So it play a role in their relationship with the photosynthetic algae, those that dwelling, inside the tissues as well. So coral is not hard. Okay, those that hard coral like stone, those are dead coral. Okay, those are dead coral. So I live in Mumbai by the sea. I had a lot of islands, several islands. I think seven, 1, 2, 3, 4, 5, 6, 7, 7 islands. Yeah, opposite Mumbai. So I went there fishing most of the time when I have free time. Like those days, yeah, those days. So I haven't been fishing for many years now. So there are a lot of coral reef around the islands. So maybe about 100 meters, 200 meters, some about 50 meters from the island itself. So it's quite huge area. So those days, people catch fish by bombing that place, right? So it destroy all the coral. But nowadays, it's been well protected. You can go there. It's not actually, you cannot go there because it is restricted area. So normally local go there fishing, for fishing. So anyway, so corals, so beautiful corals, those hard tones, white is a dead coral. Okay, and of course, sometimes you can see this biofluorescence. If you're living by the seaside, for instance, during very dark night, you can actually, or slight um, moonlight, you can see a bright color from the ocean floor, from the seawater, and all this actually the biofluorescence emitted by the planktons and so on. Right? Even some fish, because I go fishing at night, so you can see that some of the fish actually giving off emissions, very not that bright, but you can see the bright color in the water that emitted by the fish. Okay, so be observant next time. Be observant, and you actually can enjoy this beautiful, phenomena of biofluorescence. Okay. And what's the difference between chemiluminescence, and bioluminescence? You notice here the text, the text change quite dramatically. So don't worry about the text, but you still can read it. Right? If you can read it. So the chemiluminescence or chemoluminescence, this is the word chemi. This is compared to bio, right? Biochemy and bio. So both actually light emissions, right? Bio involve living organisms, plants and animals, and insects, not animal. I don't see animals that give bioluminescence unless now genetically modified animals then give you bioluminescence. You see dogs that emits fluorescence, so those genetically modified bioluminescence. Okay, chemiluminescent chemicals, chemical reaction that emits light, reaction that emit light. So two different. Uh, the bioluminescence, right? Emission of light by living organisms. Normally, it actually not in heat being evolved um, in the reaction. So chemical energy is converted to, because if the heat being evolved, of course, it might kill the plankton organisms, the insect, and so on. Right. So the process that takes its place among other spectroscopic technique because it inherent sensitivity and selectivity. So it requires basically no excitation source, right? Unlike chemiluminescence, remember we talked last time, we are talking about fluorescence emissions or phosphorescent emissions. We need to pump in energy. So you need an energy excitation well below, higher than the energy of first excited state of the chemical compound in order for you to observe the fluorescence, right? So, and secondly, only a single light detector, such as photomultiplier. This is, we talked about photomultiplier last time, so it's multiplying the signals, right? Multiplying the signals, for instance, or giving a very large signals, right? Small signals that can observe very large signals, right? And secondly, excuse me. And lastly, we need no monochromator, all right? Monochromator basically this or not even so, right? Before the light pass through the monochromator, normally you have the incident light, so light source coming in, so you have filter, right? You have filter, then it goes there, right? And this filter, it changes. Normally spectrophotometer, UV visible spectrophotometer, maybe you have like minimum of two to three filter. So when you run a spectrum, this is, for instance, the absorptions, intensity, lambda. Sorry, my nose is itchy. So you'll notice sometimes you have a slight change here and slight change. A slight, very minute. Right? This is an artifact, artifact that caused by the filter change. It goes click, 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 click. If you hear that, it means the spectrophotometer actually changing the filter. All right. Excuse me. And going back to chemiluminescence, right? Going back to chemiluminescence. This is chemical reactions, a process that giving off light energy. We have example here, the luminol, right? Luminol. So the oxidation of luminol, and the oxidation of luminol process at 5-amino 2,3 dihydro 1,4 talladiene. Okay, react with base OH, for instance, right? This is hydrogen peroxide. Okay, ferrocyanide is this one, right? I give you the chemical formula structure there for fluorescent, or um, the our 3 plus. If you have without the K here, right? Yeah, 3 plus there. Okay. Okay, here is 3 plus, sorry, 3 minus. 3 minus. 3 plus, K for 7 plus, sorry about that. So give you this intense blue light, this luminol. Okay, luminol. So I did this luminol last time when I determined the dead times of my kinetic instruments, because the kinetic instrument actually using UV visible, so use luminol to detect the dead time of the instrument, because when you mix, there's a dead time before it able to actually detect what's going on, detect the reaction in the solution. Right, the lapse lah basically is some delay. So what is the dead time of the instrument? And the species, this one that responsible for light emissions. So this is you have the species here, right? The triplet excited state, all right? The aminophthalate, right? So you have the triplet state, you have the first singlet excited state, and you have the ground state of this luminol. Okay, the oscillations. Right? This is and the cause, right? The uh, uh, unstable state of this luminol, right? And bioluminescence is one of maybe very common to you, is the firefly. So nowadays there's not much fireflies around. Right? I mentioned even in my notes. When I was young, there's a lot of fireflies that you can ask your parents in their childhood in the villages or in jungle, for instance. You can chase the fireflies and you collect fireflies those days, because so many of them, right? So many of them. Nowadays, last week, because I remember this class, so in one evening, only saw one or two of the fireflies. So it's still there, but unfortunately, I mean, we use insecticides, we use pesticides, herbicides, actually kill these all the fireflies. They're very sensitive to all this poison. Okay, and this one is the middle one, the middle one. All right, this is actually the from the plankton, and the third one, the mushroom. Um, uh, So the bioluminescence, right, generated by chemical reactions, and fluorescent, whereas is actually re-emission of transformed light that was absorbed by a substance, and then when they come down to the ground state, it emits fluorescent, right? All these living organisms, I think they actually glow by itself. You can see this, right? Very some are very bright colors. Some lipids in our country also emits lights in the evening, so we give a bioluminescence. Some lipids, okay. Some lipids, sorry, not lipid, lipids. So now, if you look at the example of fireflies, Protinus praelis, right? This is typical fireflies in our country. On the right hand side, I'm not sure about it. Maybe we have, but not very common. Okay, so this is quite typical fireflies. Not very common, right? But what I've seen mostly in different states, actually, this is the one. Right on your left hand side, bottom corner of left hand side. Right. So the light emissions in yellowish green. yellowish green, right, is around 500 nanometer. So it's 560 nanometer. This is giving a yellowish green. Right? If around 600 to 700, so maybe blue or red. Okay. So this is actually from luciferin luciferase reactions from the fireflies itself. So the light emitting reaction, this one require luciferin, adenosine triphosphate, require oxygen, right? Basically luciferase. This is a protein, right? Very large kilodalton of proteins molecules, right? This macromolecule, right, with the cofactor of Mg. This is to actually assist the reaction that produce oxyluciferin, right? Produce oxyluciferin, right? You have adenosine monophosphate, you have pyrophosphate, and carbon dioxide. So as a result, you have the light emission, right? Light emission. So what you can see is light emissions from this reaction, okay, of luciferin luciferase reaction. Okay, from these reactions, if you observe light emission. So other firefly species may emit longer wavelength. Why emit a longer wavelength? Because maybe the environment. Okay, let's see. Okay, the environments are more rigid, polar, non-polar. Okay, polar, non-polar, different conformations, different interaction with the protein molecules. Okay, and rigid environment as well as the molecule may be more rigid. Okay, that actually causing variations in the lambda max. Of emission. Okay. Don't forget, it's also pH dependent. Right? pH dependent, just like in your laboratory, right? You can observe the UV visible spectrums of your compounds. I can't remember what it was, but at different acidity, yeah. So you can get different spectrum, right? Now, going back to the Jablonski diagram, when you talk about the variations in the lambda max of the emissions, variation in lambda max emissions, the surrounding or the environments of the molecule actually play roles in whether you have blue shift or you have a red shift, right? Blue shift or red shift. So you have the hexane, right? You have water, right? Of course, this one lambda max less than lambda max of water, isn't it? Right? So in terms of energy, of course, it is higher. This one energy is lower. Okay, energy is lower. Right. So the Jablonski diagram, the absorptions in a picoseconds, right? The fluorescence in about nanosecond, right? Nanoseconds. So absorption very fast, pumping and or light absorbed, the process very fast. But the cooling or the relaxation or internal combustion, that's slightly slower than or much faster than fluorescent process. Okay, much faster than fluorescent process. In this case, the rate determining step is the fluorescence. So you can measure the decay of the fluorescence intensity over time, right? Time maybe in millisecond, for instance, right? Over time, right? So fluorescent intensity, okay, over time, right? So the molecule in S1 state is almost the same state, or almost always has higher dipole moment than the ground state, right? Higher dipole moment than the ground state. because it's located in a cage of solvent molecule in the area in the energy level S1, which include contribution from the threat interaction of the dipole with the environment. So if you have, I just draw, let's say this is our molecule, right? Not naphthalene, just an example of molecule, okay? And you have the solvent actually surrounding the molecule, a cage, right? The cage. So this is a caging effect of the molecule. So this one is water, then water lah, right? If you want water, then water. If this one ethanol or methanol, then methanol. Okay. There's a disruption here, right? Disruption of hydrogen bonding, for instance, by the presence of the molecule, right? Even in non-polar solvents, so you have this as well. So it's a cage of the solvent molecules, right? And from the Coulomb's law, the electric energy will actually bend inversely to the dielectric constant, right? Dielectric constant. So water is 80, methanol around 30, 33, ethanol around 20 to 24. Right? This is very common solvent that we use, right? So hexane, right? Dielectric constant about 2. If you mix ethanol and hexane, so it falls somewhere in between of your dielectric constant, right? So this one, longer wavelength, right? Mentioned earlier on. So the same argument can be extended to force bound to protein, bound in protein and hydrophobic activity, because protein, when you have a lot of protein in the big molecular weight, they are more hydrophobic in nature. At the same time, protein is more rigid. They are still liquid-like, but they are rigid in structure. They're still rigid in structure. So this is protein made up of amino acid. You have sequence of amino acid. You have sequence of amino acid. So this is going to be a repeat sequence and so on, right? And the amino acid that interact with the molecule in the reaction center that we are talking about just now, right? So the protein environment itself, right? The protein environment itself is more rigid. It's more rigid. This is actually causing the blue shift of the fluorescent, right? The blue shift of the fluorescent, right? And we just take example. This is our molecule, right? This is our molecule, for instance, and the bulk of the protein is this. I just give example. Okay, this is the bulk of the protein. So this center here, right, actually specific to molecule, right? Very specific to this molecule, right? Because surrounding here, this amino acid that interact with this molecule. So they are complementary amino acids that interact with this molecule. Okay, right? So on adsorptions, right, the initial state, okay, of the it goes to higher vibrational electronic state, excited electronic state, and you have a redistribution of electron resulting in an increase in dipole moment, right, of your molecule just now. Okay, and you have tighter interactions with the surrounding because you have increase in dipole moment over here. Okay, so when you have dipole moment, you like create one more positive, one more negative, right? For instance, right? one more negative, the electron moves to one side than the other, for instance. So if you have carboxylate N and you have amino N, right? This is uh, R R4, for instance, or just R2, right? No, sorry, R3 here. Okay, or just R3. Okay, because ammonia you have a lone pair of electron, for instance. So this is negatively charged. So this is towards, of course, delta positive of your molecule. This one goes towards delta negative. This is your molecule. Right? Remember, this is actually in the protein. Right? Okay. So the emission of the luciferin. This is an example that I took, okay, from this reference. The luciferin analogs comes X. So you have this luciferin analogs of the molecule that obtained from the earthworms of Blicia heliota, basically 2-carboxymethoxyvinyl hydroxybenzoic acid. Give you all this structure of molecule and the absorptions on your left hand side, emissions in a basic, more intense, right? And in basic actually shift to a higher wavelength compared to in the acid. You notice that slightly the slight variation in the intensity of the emissions. Right? The more intense in the basic compared to the acidic. Right? Now, topic to topic. Okay. And we are looking at luminol, Leon, for instance, right? And sometimes there are two processes after that can actually change these fluorescent emissions, right? So this actually helps us to understand on different in the spectrum, right? When the molecule actually in the protein environment, because it's more rigid, right? And sometimes it holds the conformation of the molecule. So it restricts the conformation of molecule, or it changes the conformation of molecule. At the same time, you have variation in the absorption, right? So flip-flopping, we're talking about boat and chair conformation. This is very fast, flip-flopping, because the molecule, they're not rigid as rigid we are talking about. They're still molecule, organic molecule. They are maybe liquid-like. They're almost liquid-like, just like any other solution. It's just that much lower proceeding times on particular conformation of the molecule. Right? In this case, we are looking at force proton transfer that occurs short lifetime, right, of the S1 state. So you have the acid-base property, right? In this case, we are talking about carboxyl or amine substitutions, then proton transfer, right? Reactions from a solvent molecule that quickly convert to initial excited state of the anion. So this is excited anion molecule, right? So the initial product of the state of the fireflies volatilization is the oxyluciferin. So these chemicals is this one, okay? And how do you attach to carbon? Next to carbonyl migrate to the carbonyl oxygen, change it to the hydroxyl group. So you have ketoenol, right? Ketoenol. So you have the enolate and the uh, enol, right? So you have OH and you have negative charge. So enolate, enolate. Carboxylate, right? Carboxylate. Okay. And if you look at luciferase itself, so when I mentioned about luciferase, need to talk about proteins or enzymes, right? That are responsible for the chemical reaction, right? In this case, the bacteria luciferase. Okay, we're talking about this is carbon structure of the luciferase, right? Bacterial luciferase. This PBD is protein database. So you Google it, internet, right? You got this structure of luciferase because a lot of library of protein in this PDP, PDP. So the bacterial luciferase that is isolate, right? Um, the emission around 490 nanometer to 509 nanometer, right? So you actually the product, so you have the flavin nucleotides. So the fluorescent Dynamac is 520 nanometer. Right? So in your lecture note, you don't have this. In your lecture note, you don't have this. So I have this in my lecture notes. Right? It's like different from your lecture notes. Okay. So the FNN person sees the slightly longer wavelength in the solvent of low dielectric constant. Right? Low dielectric constant. So in water, right? Let's say compared to water, right? Water is 80, something is lower. In methanol, in ethanol, right? For instance, right? In hexane, okay, in toluene, for instance, much lower dielectric constant. We we have our dielectric constant just now shifted a bit. Okay? So in this case, the FMN actually located over here. So we are talking about protein reaction center, just like in photosynthesis. So if you draw this, we like that. So this part area, mainly hydrophobic. One word, PHOPIC. Or like this part here, okay, this is polar, water like. Okay, so another example that from luciferase from Japanese Kenji Wataru, Luciola cruciata complex. Okay, and you can see much clearer. All right, I think if you look at the molecular structure over here, much clearer. Remember, this is actually the protein. Right, outside here actually the protein. Right, protein structure. So this is a network of protein. We don't know where it is from. Okay, this is one of the network of sequence of the protein that complements with our molecule over here. Complement our molecule over here. All right, so I just skip this. So luciferase binding site. You notice this one much clearer. I just blow it up a bit. All right, luciferase binding site. Okay, so this one molecular through molecular bindings of the bioflux luciferase, luciferin AMP, adenosine monophosphate analog. Right, the green one. So much clearer to see over here. So the rest is actually the protein sequence, right, of the luciferase, protein sequence of the luciferase. So here, over here is the This lysine, right? Tyrosine, right? Arginines, all these actually serines, all this serine over here, right? Lysine over here, arginine over here. All these actually amino acid from the protein macromolecule, right? So in this case, the interaction between uh, the molecules of luciferin, oxyluciferin, among themselves here, negative here, there's interaction between bonding, right? Maybe, right? Hydrogen bonding. So you have lone pair, right? Hydrogen, just like, oxygen, lone pair from oxygen. So you have hydrogen bonding interactions much stronger than normal hydrogen bonding, for instance. Right. So this one actually complementary molecule to this surrounding residue of amino acids of your luciferase, right? And if you look at the fireflies, or this one is much better compared to the other one. The other one I cannot see this. So this you have the speed of light, you have the responsivity, right? You have the lambda max, you have the speed of light, you have the electron, which is coulombs, 1.6 to 10 minus 19 coulombs. So speed of light, 3 times 10 uh, meter per second. Right? So if you look at the quantum efficiency, right, in this case is reached almost 100% for bioluminescence compared to chemiluminescence. Plus minus, maybe 1 to 2% only, right? 1 to 2% only. So it's more efficient chemical reaction, right? Chemical reaction. So you have the oxidation of the luciferase that is catalyzed by the magnesium, luciferin, plus ATP and oxygen. So you are giving the carbon dioxide, the AMP, adenosine monophosphates, and as a consequence, you have the emission of light. So this is what we normally observe in the reaction, right? Reaction. Right. Okay. Right. That's it for now. So let's cover up until 10 to 10. Right. 10 to 10. Okay, guys. So thank you so much. So please, I think I'll prepare. I think next week I'll prepare for your add puzzles and class tutorial, class test, simple test. Add puzzles is something related to the work, right? I post it and you do it on the same time of your class. Do your add puzzle first, so those tests you can do it at home and submit, right, in the Google questions. Okay, so thank you everyone.